Welcome to the season 2 of about creative uses of AI in Norway. Now, let's go to my human counterpart to introduce what will happen. Make sure to stick around to see how ChatGPT reacted to the last scene that was made in Blender.
I am your host, Ali Sobot.
Don't be a prick. Make sure to like, comment and subscribe.
Season 2, Episode 8 of Creative Use of AI in Norway. First, we're going to goof around neural networks and then start with the creative parts of this episode. Before that, let's make a recap of last episode. Based on David Chapman's study, neural networks are machine learning tools modeled after the human brain to identify patterns and make predictions. At their core, these networks function as a web of interconnected layers where individual nodes, artificial neurons, act as the primary processors. In the context of large language models, generating specific text like artificial neuron or a text like I hear you, these nodes function as a detective's office. Each node receives incoming signals, or clues if you will, weighs their importance and determines if the signal is strong enough to fire. This process, known as activation, is a pivotal moment where the network transitions from analyzing raw data to making a specific decision, resulting in the precise generation of letters and words. Conclusively, ultimately the power of a neural network lies in this collaborative web of nodes. By mimicking the biological transmission of information, these artificial neurons transform complex mathematical patterns into coherent human-like output, effectively copying the homework of the human brain to solve sophisticated digital problems. Now we will make an effort to test the hypothesis and answer the following question based on Chapman's understanding. FYI, this is a question I asked earlier in earlier episodes. I think it was first or second episode, I'm not sure. So the hypothesis. Deep learning refers to networks with multiple hidden layers. And the question is, when we are talking about multiple hidden layers, are we talking about neural networks? Are they neuron layers? So Chapman argues, deep learning, and this is a quote, deep learning is a subset of machine learning, has at its foundation several critical concepts that enables the training and operation of neural networks. Neural networks are computational models inspired by the human brain that are capable of learning tasks by considering examples without being explicitly programmed to perform the task. Hidden layers can learn highly abstract representations of data. This deep architecture is the defining characteristic of modern neural networks, hence the term deep learning. The development of deep learning has led to dramatic improvements in task spanning. So here's my reflection. Deep learning is a subset of machine learning. So earlier, right before I said this is my reflection, I closed Chapman's quote. So here's my reflection again. Deep learning is a subset of machine learning, or ML, that helps in training and operation of neural network. Hidden layers help the process of deep learning with highly abstract data in order to improve the task spanning of neural networks. Now let's have a one-to-one with Gemini. Howdy. Can you simplify both Chapman and my code so that not just my audience, but me also understand better what my own points were?
Imagine you are teaching a computer to think, but instead of giving it a giant book of rules, you are building a robot brain. Here is how that robot brain deep learning actually works. 1. The big club and the small club. Machine learning, ML, is like a big club, where computers learn to find patterns in data. Deep learning is a special, smaller club inside that big club. As Dave Chapman explains, deep learning, a subset of machine learning, involving deep networks, has gained immense popularity for its ability to process and learn from large amounts of data. It is the specific part of AI that uses neural networks, which are basically a collection of connected units or nodes called neurons, which loosely model the neurons in a biological brain. 2. The hidden layers are like factory floors. Think of a neural network like a giant factory with many floors. The first floor is the input, where you put in information, like a picture of a dog. And the last floor is the output, where the computer says, "That's a dog." The floors in the middle are the hidden layers. In simple networks, you might only have 1 or 2 floors, but in deep learning, you have tens or even hundreds of these hidden floors. These layers are the engine that allows the computer to do a lot with as little help as possible. 3. Understanding abstract information. How does the computer go from seeing a bunch of colorful dots to knowing it's a dog?
Wait. Not so fast. Can you give me an example of highly abstract representations of data in the deep learning process? And also, to anyone who's following this, if you've got any questions, just write it in the comment section, and maybe that could be the topic of next episode.
In the context of deep learning, highly abstract representations of data refer to the complex concepts that a neural network understands after processing raw information through many layers. Instead of seeing just pixels or letters, the network builds a hierarchy of features where each layer identifies increasingly complicated patterns. Here are specific examples of highly abstract representations found in the sources. 1. Visual abstractions, image recognition. When a convolutional neural network, CNN, processes an image, it doesn't see a face all at once. It breaks the task down into layers of abstraction. Low-level, concrete. The first layers detect simple edges and textures. Mid-level: the middle layers combine these edges to recognize motifs, patterns, or parts of objects, like a nose or wheel. High-level, highly abstract: the deepest layers concatenate these features to identify complex objects, faces, or scenes. As Dave Chapman notes, as data passes through each successive layer, the network learns hierarchical features with high-level more abstract features, building upon the lower-level ones. 2. Language abstractions, NLP and LLMs. For large language models, LLMs, like ChatGPT, the abstraction moves from raw characters to human-like understanding. Low-level: the network identifies individual letters or tokens. Mid-level: it begins to recognize syntax and grammar rules. High-level, highly abstract. At the deepest levels, the model understands semantics, meaning, sentiment, emotions, and context. For example, the network can discern that the word trunk refers to a part of a tree rather than a car based on the abstract relationship it has formed with the surrounding words. 3. Latent space, autoencoders. In unsupervised learning, an autoencoder compresses data into what is called a latent space representation. This is a highly abstract bottlenecked version of the data that ignores noise and only keeps the most significant attributes. A highly abstract example here would be a style or identity that the network can then use to reconstruct an entire image or generate something new. Why are these abstractions important? As Chapman explains, these additional layers allow for the modeling of more complex relationships in the data. This ability to form abstract thoughts is exactly what allows AI to move beyond simple math and perform tasks that once seemed exclusive to human intelligence, close quote, such as mastering game strategies through trial and error or creating realistic synthetic images.
Okay, thanks. Can you explain this image? What are all the visual cues, inputs, input layer progressions, and whatever we are seeing on the screen right now?
Key elements visualized: the input chaos, raw pixels and characters entering the digital archway; layer progression, the evolution from simple lines to complex cyber-organic patterns; the abstract concept, a multidimensional face forming in the deep hidden layers; the single neuron, the summation symbol $, sigma $, and the activation function pulse at the heart of the processor.
Okay, thanks. Now, I want you to nuance my reflection and melt it with David Chapman's understanding. Just to remind the viewers, my reflection was the following. Deep learning is a subset of machine learning, ML, that helps in training and operation of neural networks. Hidden layers help the process of deep learning with highly abstract data representation in order to improve the task spanning of neural networks. Yeah, your turn.
To nuance your reflection and blend it with Dave Chapman's technical insights, we can look at deep learning not just as a helper for neural networks, but as a fundamental shift in how machines handle complexity. Here is a more detailed breakdown, merging your thoughts with the sources. 1. Depth as the defining characteristic. You mentioned deep learning is a subset of machine learning ML, which is correct. However, Chapman nuances this by stating that the defining characteristic of modern neural networks is their depth. Specifically, having multiple hidden layers. While a shallow network might only have 1 or 2 layers, deep networks often have tens or even hundreds, allowing them to model much more complex relationships than traditional ML. 2. The move from manual to automated learning. A key nuance to your point about training and operation is automation. In traditional machine learning, a human expert must manually identify features, specific traits in the data for the computer to look at. Deep learning changes the game because it automates the feature extraction process. It allows the model to find representations within raw data that might be less obvious or subjective to a human expert. 3. The engine of hidden layers. You noted that hidden layers help with abstract representation. Chapman expands on this by explaining that these layers are the engine, or the core processing zone. The process. They are hidden because they are not directly exposed to the input or output. Instead, they capture and transform the underlying structure of the data. The result as data flows through each layer, performs a specific math operation. It takes weighted inputs, sums them up, and applies a nonlinear activation function to decide what to pass forward. 4. A hierarchy of understanding. Your mention of highly abstract data representation is what Chapman calls a hierarchy of understanding. This is how the network thinks through the layers. Early layers detect simple patterns, like edges, lines, and textures. Middle layers combine those edges into motifs and geometric patterns. Deep layers, finally, assemble these into high-level abstract concepts and recognizable objects. 5. Why task spanning improves. Finally, your point about improving task spanning is rooted in the network's ability to model nonlinear relationships. Early AI was limited to linearly separable problems. Simple straight-line logic, which caused a decline in interest, known as the AI winter. Deep learning's ability to use multiple layers of nonlinearity is exactly what allowed for dramatic improvements in task spanning beyond image recognition, including natural language processing, speech recognition, and complex game strategies.
Thanks. Okay. Yeah. Okay. Thanks, Gemini. But you really didn't have to take a shit all over, or to take a shit all over my reflection, though. But I guess it's okay, because that's why you are here. Nuancing is basically correction, thought correction. That's how I interpret nuancing. So I really don't mind that Gemini basically ripped away my reflection into pieces. That's That's their function. Thank you for anyone watching, and see you on the flip side. Oh, and before we go on the flip side, what's going to happen in part 2 is that I have continued the storyline of Last Blender animation. Also, if you're impatient and basically you know your way around Blender and don't need any guide, so the Patreon page is for you there to basically download all the resources you need to get the entire workflow. Also, if you find any value of what I'm making, hit that like and subscribe button. Especially the tutorials are quite resource intensive and actually make a lot of time to create. Thanks in advance. See you in part 2.
Now let's jump right into part 2. The scene is incorrect as ChatGPT was punched by me, so ChatGPT is reacting, not me. The Blender file is correct, but the tutorial scene is wrong. You can still apply the commands. Here is the actual scene I made, but I didn't have time to make another tutorial, which would be pointless. Blender Essentials for creating and animating your own character. How to create hotkeys for Blender. Right-click mouse on the GLB GLT file format. Change, create shortcut. I press plus to jump into importing. You do what you want. Plus and import your first character. Delete unwanted artifacts. Press X. Double-click on Armature to rename. Rename to Actor 1. Animate your actor. Add new animation. Adjust timeline. Combine animations. Add new actor. RZ. Double-click on Armature to rename. Delete unwanted artifacts. RZ. Delete keyframes. Drag the plus from the corner. We need new screen on Blender. Change the screen to NLA. Change the other screen to Dope Sheet Action Editor. In the action editor, find your animation. I've got 2 of them here. Choose your actor, then choose your animation in Action Editor. Combine animations. Widen NLA screen, mouse wheel up and down. Find the data. Add new animation. RZ to adjust animation armature. Choose the actor. Choose the animation in Action Editor. Rename animation to backflip. Adjust timeline. Push down animation to NLA. Put the animations on their places. Adjust the strip extrapolation. Nothing. Blending. Combine. The same with your other animations. Add texture, link to Texture Central on the description below. Way too dark. Let's go to world and adjust the lighting. Right-click on the X, Y, or Z. Click on the buttons on the side panel to change angle. Mouse wheel up and down for zooming in and out. Grab the hand symbol to go up and down like this. Bro is blind. Let's fix it. Switch on the X-ray. Let's find the eyeballs. There we go. Go to the transformer section. Change the location on the Y-axis to see the eyes. I know approximately where I should position them. The smart thing is, however, to switch off the X-ray vision and to actually see shit. See what I mean? Let's zoom out and see what we are working with. WTF? Let's go to the timeline. Fix it to 95 frames. That's how long the animation lasts. The T position sucks. Let's fix that. Change the frame start to 0. Let's clean the screen for a screen record. Oh wow, thank you for watching. I absolutely can't wait to hear all about where you're tuning in from in the comment section below. And of course, just because I'm Alice AI version doesn't mean your comments aren't wildly important. Make sure to like, comment, and subscribe.